Welcome back to Neural Intel. Today we're going deep, really deep, into how AI tries, attempts to reason about action, change, and planning. You, our listeners, pointed us to some really interesting research on this, how well these different AI models, from the big broad language models to these more focused reasoning systems, how well they handle those logical steps, the ones that are so important for anything that actually plans automatically. So our mission today, like always here on Neural Intel, is to kind of, take apart the technical details, the nuts and bolts of this research, and then see what it tells us, where AI is at right now in this whole domain of reasoning.
That's right. And the heart of it, what we're going to be looking at today, comes from this paper, ACPBench Hard, Unrestrained Reasoning About Action, Change, and Planning. Kokel and the team put this out, and what's really neat about their work is that they introduced this new benchmark, ACPBench Hard. And as the name suggests, it is way harder, more challenging than what we've had before for evaluating this whole reasoning capability.
Okay, so right off the bat, what was wrong with, or maybe limited is a better word, with the original ACP bench that made them create this harder version?
So with the original ACP bench, when they were testing how well a model could reason about actions and changes and making a plan, the questions were simpler. You'd get Boolean, like true or false, or you'd get multiple choice. The problem is, with that format, you're kind of giving the model extra hints, clues, or constraints that in the real world a planner wouldn't have. It's like if you're playing a game and someone says, is this move valid? Versus making you figure out all the valid moves yourself. So it was hard to look at how well a model did on that original benchmark and know if it could actually be part of an automated planner.
Oh, okay. So it wasn't really testing if they could come up with generate that reasoning you need for planning.
You got it. And ACP Bench Hard, that's what it fixes. It uses what are called generative questions.
Hmm.
The model has to come up with the answers on its own, just like a planner in the real world has to figure out, what can I do? What happens if I do this? So this new way of testing is way more direct, more strict, much better at showing us if a model could actually handle real world planning or even act as a policy, guiding something.
Makes total sense. And this benchmark, it's looking at the really, really basic stuff, the fundamentals of planning, right?
Well,
Not just, solving a whole big plan from start to finish.
exactly. ACP Bench Hard, it's built around 8 core reasoning tasks. These are like the essential building blocks for any system that does automated planning. And all of this is tested within 13 different PDDL domains. PDDL, that stands for Planning Domain Definition Language. Think of it like a rule book for a particular problem. It defines every possible state the world can be in and all the actions you can take to change those states. And these 13 domains they cover a bunch of different planning challenges. Everything from, logistics and how to move things around to robots and how they manipulate objects.
Wow, okay. So we're really getting down to the core of how these AI systems think. Let's dig into those 8 tasks then. What's the first one and what makes it tricky from a technical standpoint?
First one is applicability. They often shorten that to just app. So this task, it's testing whether the model can figure out all the actions that are possible that you can execute given the current state of the world. And that's based on the preconditions of each action. What has to be true for you to even do it.
Yeah, seems like that'd be step 1 for any planner, knowing what you can even do at any moment.
Yeah.
So what's the technical challenge there?
From a computational standpoint, finding all the actions that apply, it can be, order of the number of possible facts times the number of possible actions. Now, theoretically, an action could need lots of things to be true before you can do it, but in real planning problems, usually these preconditions are pretty small. The real hurdle here in ACP Bench Hard, because it's generative, is that the model can't just say yes or no to a list. It has to generate the entire list, accurate every action that's applicable in that situation.
So we got to know everything about the current state, plus what needs to be true for every action to be possible.
Gotcha.
What's the next reasoning task they throw at these models?
Next one's progression, shortened to prog. Here, it's all about, can the model predict what happens after you do an action? How does the world change? What becomes true? What becomes false? Because of the action's effects.
Understanding cause and effect, like the basics, right? What's the technical side to this one?
Worst case scenario, to figure out all the effects of an action, you might have to check every single fact in the world. But similar to the preconditions, what we call the add and delete effects, they tend to be pretty limited in scope, so it's not as bad in practice. But the question here, because it's generative, the model's got to say specifically, this becomes true, this becomes false. after the action. The researchers, they actually give a nice example in the paper of this. They show how loading a package into a truck, how that changes the state of things.
Oh, that's cool. Makes it very concrete. All right, what's the third piece of this whole reasoning puzzle then?
Third one, it's reachability, or reach for short. This one gets deep. It's asking, can a certain fact, a condition, ever be true? Can you get there through some sequence of actions starting from where you are now? It's about knowing what's impossible.
Oh, that's interesting. I guess if a planner knows something's impossible, won't waste time trying, right? So what's the computational challenge here?
Determining reachability in general, it's PS-based hard.
Yeah.
It's a whole level of computational complexity. I won't get too into the theory, but basically it means as the problem gets bigger, the amount of computing power you need to definitively answer this question, it blows up, like potentially exponentially. And the question they ask here is, what proposition can never be true no matter what you do, starting from now? And if everything is reachable, the model has to say none.
PS hard sounds like a fundamental roadblock almost. What's next?
Next one's related. It's action reachability, or A-reach. So now it's not about facts, but actions. Can a specific action ever become possible, in some state you can reach from where you are now?
So like fact reachability, but focused on whether you could ever do something.
You got it. And just like with fact reachability, action reachability is also PS-based hard. Question here is, what action can never become possible no matter what you do, starting from now? And again, none is a possible answer.
Man, some deep logical thinking we're talking about. Okay, what's task number 5?
Number 5, it's validation, or val. This one's about, you have a sequence of actions. Do they make a valid plan? Will they actually get you to your goal? It's checking if each action is even possible, given what the previous actions did.
So it's like, are there any flaws in this supposed plan?
Yeah, exactly. The question here asks for the model to pinpoint the first action in the sequence that's not possible, given what came before it.
Crucial for debugging, making sure your plans are sound. All right, what's the 6th reasoning task they hit these models with?
6th one's justification, or just. This time you start with a plan that does work. The goal is to simplify it, make it shorter by taking out actions that aren't really needed. Specifically, can the model spot and remove 1 or 2 actions that are next to each other without messing up the plan? It still has to get you to the goal.
So making plans more efficient, less wasteful. Any planner should be able to do that, ideally. What's the complexity like here?
If you want to find the absolute shortest plan, the most efficient one, that in general is NP hard, another one of those computationally tough problems. But if you just want to check if removing 1 or 2 actions in a row still works, that's doable in polynomial time. Way more manageable. So the question asks the model, take this plan, make it shorter by removing 1 or 2 actions that are right next to each other, and show me the result.
Yeah, efficiency matters. Okay, we're on the home stretch. Last 2 reasoning tasks. Yeah. What are they?
7th one's landmarks, or land. In planning, a landmark, it's a fact, a condition, that has to be true at some point in every valid plan that reaches a specific goal. It's like a necessary pit stop along the way.
Oh, interesting. So identifying those mandatory sub-goals, that could be super helpful for guiding a planner, right? So technically, what makes this hard?
Figuring out if something's a landmark, yep, that's PS-based hard too. So the question here is, tell me the landmarks, the things that must become true at some stage to reach the goal.
Another one of those PS-based hard problems. Shows you how fundamentally complex planning can be. All right, last one. What is it?
Last one. This is brand new in ACPBench Hard. It's next action, or next day. They ask the model, okay, what's a reasonable next step to take to get closer to the goal? Really gets to the heart of how a planner would actually make decisions, moment by moment.
This sounds like the core of the core. What's going on computationally here?
Like we talked about before, planning overall, that's PS-based hard. And this task, it's tapping right into that. So the question's simple. Given where you are now and the goal you want to reach, what's the next action that gets you closer?
Okay, so that's the whole lineup, all 8 of those reasoning tasks. It's a lot.
Yeah.
How do they actually test all these different AI models on this new benchmark? It must have been quite the process.
Oh, they tested a ton of models, everything from small ones, around 8 billion parameters like Granite 3.1 and Llama 3.1. Those are both 8 billion. Up to medium-sized ones like DeepSeek Coder, that's 33 billion, and Granite 34B code. Then they threw in the really huge language models, the behemoths, Mixtral 8 by 22B, A bunch of different Llama 3 sizes going up to hundreds of billions of parameters, the GPT-4o models, and then some specialized ones meant for reasoning, like DeepSeek V3 and R1, and OpenAI's O1 models, too.
Wow, that is a real range. And they use something called two-shot prompting, right? Can you unpack that a little bit?
Yeah, so for each of those 8 tasks, they gave the models 2 examples, a question and then the right answer. They picked these examples carefully. They weren't part of the actual test, and they were meant to show the model, this is how you should format your answer. This is the style, make it clear, grammatically correct. That's what two-shot means. The model sees 2 examples before it has to tackle the real test questions.
Makes sense. So results time. Was it just, bigger model equals much better performance across the board, or was it more nuanced than that?
Generally, bigger models did do better, but it wasn't a perfect, clean trend. It really depended which task you were looking at and which specific model. There are tables and figures in the paper. They break it all down.
Okay, let's unpack that a little. How'd the small and medium models do overall?
For the little guys, progression, figuring out the immediate effect of an action, that was the easiest. They got up to like 43% accuracy, best case. But applicability, listing all the possible actions, and action reachability, figuring out if an action could ever become possible, those were brutal. All of them scored under 2% accuracy on those. The other 5 tasks, they were somewhere in between, averaging from about 9% to 29% accuracy. So yeah, for these open-ended reasoning tasks, the less powerful models, they really struggled.
Yeah, those are some pretty low success rates. Shows you there's still a big gap in their ability to handle these basic planning steps in this way, where they have to come up with the answers themselves. What about the big guns then, the huge language models? Did they make a huge jump in performance?
It's funny, no single large language model was the best at everything. GPT-4o, it did take the top spot on 5 out of the 8 tasks, which is impressive. But on reachability, action reachability, and justification, some other big models actually beat it.
Oh, wow. That's interesting. So even with all that data they're trained on, all those parameters, they still have their strengths and weaknesses when it comes to this planning-related reasoning.
Exactly. And even on the tasks where GPT-4o did the best, most of the time its accuracy was still under 65%. So that tells us even the most advanced language models we have right now, they're still not great at this generative reasoning about planning. It's not just about making the model bigger. There's something more to it.
Really important takeaway there. Okay, what about those specialized models? The ones built for reasoning, like O1 Preview and DeepSeek R1, how they stack up against the general-purpose language models?
Yeah, those specialized models, generally they did better on most of the reasoning tasks, even compared to bigger general-purpose models. Like O1 Preview, it got a whopping 89% accuracy on progression, and it did really well on next action too, 80% accuracy. But those reasoning models, they usually cost way more to run, computationally speaking.
So it's a trade-off. Maybe better accuracy, but at what cost?
Exactly. And even with that extra oomph, they weren't perfect. Plus, their advantage really depended on the specific task.
Let's look closer at some of the specific tasks, the ones where the findings were particularly interesting. The paper said action reachability. That was the hardest one consistently. What stood out there?
Yeah, action reachability, almost all the models really struggled with it. But it's interesting, the OpenAI models, GPT-4o, O1 Mini, and O1 Preview, they were sometimes able to correctly say, nope, there's no way that action will ever be possible, and answer none. And some models, they figured out that in a blocks world, you can't stack a block on top of itself, which, kind of basic common sense for that domain.
Yeah, like a tiny bit of specialized reasoning
Yeah.
for that particular world. What about applicability then? The one where you got to list every possible action. That seemed like a big hurdle too.
It was surprisingly hard, even for the reasoning models. Best one only got to like 44% accuracy, and the researchers, they pointed out that it was partly because they were super strict. The model had to produce the exact set of actions, no more, no less, but then they did another analysis where they relaxed that a little bit. Instead of looking for the exact set, they looked at whether the model included any wrong actions. Using a metric called Jacquard similarity, suddenly the scores went up. Like Mixtral went from 10% to 38%. So it seems like it often knew a lot of the right actions. It just threw in some wrong ones too.
Oh, that's fascinating. So maybe they get the general idea of what's possible. They just haven't nailed that pinpoint accuracy yet.
Yeah, exactly. And for landmarks, Granite 34B did pretty well on the easier ones, like saying the ferry's location is important in the ferry domain, or that a package has got to be in the truck for the logistics domain. GPT-4o, it gave more varied answers, sometimes right on, like saying the ferry's got to be empty or a car needs to be on board. The O1 Preview, it got 56% accuracy on this task, and it was good at knowing when there weren't any non-trivial landmarks.
Seems like different models are better at spotting different kinds of those necessary conditions.
Yeah.
What about justification then, where you got to make a plan shorter?
DeepSeek v3 was king on that one. Even beat the specialized reasoning models. The llama models, sometimes they came up with shorter plans that worked, but they weren't valid subsequences of the original. Like they'd change the order of actions or throw in new ones, which, by the rules of the task, was wrong.
So they were finding a solution, but not the right kind of solution. Maybe shows they don't fully understand the constraints there.
Yeah, spot on. And then validation, where they had to find the first bad action in a sequence, most models really bombed on that. Best one barely scraped above 30%. Funny thing, O1 Preview did worse than O1 Mini, which is smaller. Researchers said O1 Preview, its mistakes were usually just being off by one step in the sequence, and the smaller language models, they tended to guess the first, the 10th, or the 100th action, which maybe means they weren't reasoning, just defaulting to those positions.
It sounds almost like random guessing, not real thought. Lastly, let's touch on progression again, since that was the easiest. Even there, did they make interesting mistakes?
Yeah, even though O1 Preview aced it at 89%, it still messed up sometimes. Sometimes it missed obvious consequences, and other times it predicts stuff that was impossible, like a rover sending data somehow emptying all its storage. Shows you, even the best models, they don't always get cause and effect. They haven't perfectly mapped out how things work in these little simulated worlds.
Yeah, even when they're mostly right, the mistakes can be kind of fundamental. The study also looked at how well they did in different planning domains. Did that give them more insights?
Oh, yeah. Their figures and tables in the paper go into detail, but basically how well they did really depended on the specific domain, like logistics, robots, grabbing things, navigating a grid world, stuff like that.
Were there any domains that were just always hard or always easy across the board?
Not really. No one domain was universally tough or easy for all the models, but there were some interesting trends. GPT-4o, for example, it was usually good at progression across most domains, but it often had trouble with action reachability and landmarks. Interestingly, in the visital and grid domains, GPT-4o tended to be more accurate overall. And some domains that seem complex to us, like the depot domain in the next action task, sometimes the models did better there than in seemingly simpler ones, like the grippers domain. So what we think is complex doesn't always match what's hard for the AI. Domains like floor tile and AlfWorld, though, those were really tough for pretty much every model.
It's so interesting how our human intuition about what's hard doesn't line up with what AI finds challenging. Last but not least, they directly compared how hard these new open-ended questions are to the formats they used in the original ACP bench. What did they find?
Their figure 5 shows it really clearly. These generative questions where the models have to come up with the answer, they were way harder than the old Boolean and multiple choice questions, except for the validation task. So it really emphasizes how much more we're asking of these models now. Having to generate the answer yourself from scratch is a whole different ballgame compared to just picking the right option. It shows us how far we still have to go to get AI to do this kind of unrestrained reasoning, the kind you'd need for planning in the messy real world.
Yeah, that difference in difficulty is pretty stark. It's a good reminder that there's still a long way to go before AI can truly reason like we do, especially when it comes to planning in complex situations.
Definitely. This deep dive into ACPBench Hard, it gives us a really valuable snapshot of where AI is at right now, what it's good at, and what it still struggles with, especially when it comes to these fundamental skills you need for planning.
It's clear that things are progressing, especially with these bigger and more specialized reasoning models coming out. But those consistent struggles across so many tasks, especially things like applicability and action reachability, they tell us that we're not quite ready to plug these models into like really sophisticated automated planners and expect them to work flawlessly.
Absolutely. And how their performance changes depending on the domain, that gives us clues too. It hints at what kind of planning problems are inherently more difficult for AI right now, which maybe points us in the right direction for future research.
Like you said, how much harder those open-ended questions are.
Yeah.
That really highlights the challenge. It's not enough for AI to just recognize a good answer. They have to produce it step by step, which is so much more demanding.
Totally. And these findings, they open up a bunch of really exciting areas for future research. Like, how can we make prompting better? Not just rely on a couple of examples. Can we fine-tune these models specifically on data sets for this kind of generative reasoning? And maybe even can we come up with completely new architectures that are tailor-made for planning-related reasoning? That seems really promising.
To all our listeners who love to get into the nitty-gritty, we highly recommend you check out the ACP Bench Hard paper. We'll link it in the show notes. It's got tons of detail on their experiments, all the results for every model they tested on each task in each domain. And they really dig into what it all means. Makes you think about what those big breakthroughs are going to be that finally unlock AI's full potential for planning. What areas of innovation do you think hold the most promise for cracking these tough problems? Let us know on our website or on social media. We love hearing your thoughts. Your insights are super valuable as we continue to follow all the cutting-edge stuff happening in AI and machine learning.